The first and possibly most common application to start with on a STEPScope is the TDR, the time domain reflection. I'm going to run just a simple experiment here where I'm going to move the reference plane to the end of this cable and then make a measurement of a DUT. To do that, we have to activate the pulsar so that it pulses output signals, and then we'll have to look at it as it comes back in the time domain. We'll use the TDR feature of the analyzer. Remember, we've already taken a peek at the square wave that would come off of a perfectly terminated sine into the step response. But for the TDR view, before we can really make any measurement, we have to first perform the reference plane calibrations. So to perform a reference plane calibration down here, it has the two steps we have to do: calibrate a short and calibrate a termination. So I'm going to first run a calibration of a short. So I will then find a short that I'm going to use one of our calibration kits here and screw a short into the end of this cable. That will define the reference plane, if you will. And I'll press the OK button here, and it'll go about and makes a measurement. We can see that up here as it progresses. It makes this measurement across all zoom levels and pan levels, different than some earlier TDR instruments where every time you changed a view, you'd have to get a new reference calibration. This one, you get the reference calibration. It does depend on the pulsar settings, but so as long as your pulsar is the same frequency and amplitude, you don't have to gain a new reference plane calibration. But that one's done. That has my termination, or now it's asking for a termination cal. So I'm going to take off this reference short, and I'm going to go to a reference termination. I will connect that termination here. This termination is 50 ohms. If it's slightly not 50 ohms, you can actually adjust that right here. That's so that you can use more readily available terminators that you might find in the open market. But 50 ohms is a good starting point. I'll press my calibrate termination number here, and it instructs me to put that in. If I was using differential, I would have both of them terminated to 50 ohms at the end of the reference plane, just like I would do the same with the short. But that is now measured, and in fact it shows me a green line here straight across at 50 ohms. That's by definition. I've just defined it to be the fact that this is 50 ohms at this point. So now let me go ahead and put some kind of a DUT on here. I have a simple DUT. It has a chip, a small printed circuit board trace, a small cable, and even an adapter. So we'll just use that for this simple experiment. So I'll connect that to my reference plane here, and then I'll go ahead and make a measurement. I could either run a single measurement or a continuous measurement. Let me run single just so we see it once. In the single, what we can see is that we have a certain activity, and then the line is dead for a long time. That tells me that my pulsar period is waiting around for reflections for far longer than any reflection would actually happen. So I could speed up my pulsar in this case. It's presently set to the default value. Down here you have the pulsar width value, and it's at 10 megahertz. So I could speed that up if I wanted to, but I won't for this test. But I am interested more in that area of the view, and so that gets to the question about the time offset, or the time span that we're looking at, and the record length. So I will go ahead and say that I'd like to only look maybe to 5,000 picoseconds, or 5 nanoseconds. So in that case, I can just change this number to 5,000 and hit enter, and it actually zoomed out there, and you saw it blocky at first, and then it makes a new measurement using all the number of points you've asked for, 1024, between this point and this point. So now I have much finer resolution. I could have also done that using the tools here. For example, I have panning and zooming. If I was to set zoom here and move to the right, I could move over here maybe to 2,000. I can also go up and down and move it vertically. And then it'll take a new measurement and redistribute the 1,000 points in that area. So this gives us our time domain view. I could turn on cursors and go ahead and make measurements of cursors, 46 ohms, 50 ohms. I can see anything above the 50 ohm line here. These are all inductive elements, and these are capacitive elements, the ones below there. So this is a big inductive spike, for example, right here. If I was to run this live run, you can see this update rate here, 4, 5, 7, 8, 9. This is how often it's updating. And you can see in an earlier video I commented about averaging, that we really don't need averaging. This is a very precise waveform, and it's remeasuring it again and again. If I took my finger and I touched this trace right at one spot, you're going to see me move my finger down that trace where I can affect the capacitive coupling. That's why it's going down. My finger's capacitive. If I let go, it'll go back to the regular measurement. That inductive spike is the wire bond inside the package going on to the on-die termination. Like all our graphs, we can download those into a CSV file and see that in great detail for every picosecond we wanted. The speed and time of that measurement is really based on the two things, the pulsar setting and the number of samples I want. So for example, if I went to 512 samples, it would run twice as fast. And if I changed my pulsar to be twice as fast, it would run twice as fast. So I could get this to run 4 times as fast by changing this pulsar rate and my sampler rate. Pulsar rates can't be too fast. They have to be able to see the entire duration of your reflected image. But for some manufacturing applications, you can see it'd be helpful to be able to tune that to get you measurements as fast as possible. Time can also be measured on these by using your X cursors. So for example, from the point at which I go through that, this is the barrel connector I've used to adapt the sex right here. And then this would be the pin inside the SMA connector. If I wanted to measure from there to, say, the other end of that cable, that was 1.1 nanoseconds. Now this is round trip time. You have to always think of that. So the actual time would be half of that. So say 550 picoseconds, maybe about 5 inches, and that's about how long that cable is right there. Okay, so that's a good quick introduction up to the point of TDR analysis. Before wrapping up this quick view of TDR analysis, I just wanted to jump back to the step response view and rerun this analysis. Remember, the step response shows us the full square wave of what we're seeing. This does not interpret it as it would be interpreted through the TDR viewer, but you can see exactly what happens in the time domain response. The fast edge has been sent down the cable. Some reflections have come back because of that DUT, and then it goes dead. Again, you can see that I could have had a pulsar way faster than this and still been able to resolve all of that information. Okay, so that was a quick view on the TDR analysis. We'll go on from there in future videos.